So hello everyone, good afternoon on behalf of the India EU ICT Standards Project. This is Sachin Gaur and I would like to extend a warm welcome to all of you. Today it's our 28th webinar in the knowledge sharing series that we run with our partners HC, which is the European Telecom Standards Institute, and TSDSI, which is the Telecom Standards Body of India. And I have a privilege today that we have some of the top experts in the field of visual light communications. We have Professor John Cosmas, Professor Anand Srivastava, who would be making two presentations. And we also have Mr. A.K. Mittal, who represents TSDSI. He's going to moderate the session. So a warm welcome to all of you, and just small introductions. You will find the exact details on our project website about the talks today, and also detailed bios of our speakers. But let me just give you short perspective in case if you are not familiar with the experts from today. Mr. A.K. Mittal, who is going to moderate this session, he is currently working as an advisor to TSDSI, basically on topics linked with 5G. But he comes with I would say quite a long background in the domain of telecommunications, working in various government positions with Department of Telecom. I think his career already spans over 45 years. And he's one of the top experts, or at least a go-to expert for me when it comes to all topics related to 5G. So, warm welcome, Mr. Mittal. Professor John, on the other hand, comes from UK. He's a professor of multimedia systems in the College of Engineering, Design and Physical Sciences at Brunel University, London. Professor Cosmas also has a long background, coming with a strong research background. He has been part of 12 research projects which were EU projects, and he has led been part of several other projects. He leads a team of 5 PhD students where they're concerned right now with management of heterogeneous visible light communications and millimeter wave networks for low latency broadband in buildings, Internet of Things for health and safety systems. Professor John also has some personal connection with India. So a warm welcome to you, Professor John, and we look forward to hear from you more.
Thank you.
Professor Anand Srivastava, who is professor in EC department in IIIT Delhi. Professor Anand, before joining IIIT, he was having positions at IIT Mandi and also IIT Delhi. And he also comes from a very strong hands-on practical background where he has worked in past with organizations like CDOT. He was part of the board of CDOT, and he has done some of the fundamental work which I think is quite important today for India. Some of you may be familiar with GPON. So we also look forward to hear from you, Professor Anand, today. And I think it's quite a honor and pleasure for me to hear from the top experts. And I think this topic is also very interesting. So let me invite Mr. Mittal to say a few words about the importance of this topic today and to open the session. Over to you, Mr. Mittal.
Thank you very much, Sachin, for this introduction. And so the topic VLC and Internet Radio Right, we are bringing to the audience because VLC is gaining importance and it has now come close of getting integrated into the telecommunication networks. And just to give you a background, and many of us may be knowing that in very old days, the shining surfaces were used to reflect sunlight to send signals. Then sometime later in 18th and early 19th century, there was Morse coded light modulation for sending messages over long distances. So that is a long history of voice communication, but that is not relevant today. We came to optical fiber communication in late 20th century. Somewhere in 1970s, we started optical communication using laser. And then now with the so much expansion of mobile services and growing requirement of bandwidth and services which require huge bandwidth and low latency, and so many applications are dependent on these aspects. So voice, this VLC is gaining a lot of importance. A lot of research has happened. Some standards work also has happened on this. And a word which we are familiar with, Wi-Fi. So VLC has a system called Li-Fi, which works more or less similar to Wi-Fi, but definitely technology is different. So this very interesting field, and I will not take more time between you and our eminent speakers. So first, I request Professor John Cosmas to please take the floor, make his presentation. And we expect, so the structure would be like that. We have about 20 minutes presentation from Professor Cosmas, then about 20 minutes from Professor Srivastava. In the end, we have the question answer session. So you can put your your questions in the chat box, Q&A box, and we will take those questions in the end. So over to Professor John Cosmas.
Thank you. Okay, I'm John Cosmas from Brunel University, and I was the technical leader of a European research project called Internet of Radio Light, and its aim was to produce radio communications access points consisting of combined visible light communication and millimeter wave multi-component carrier architecture, and to see how it performed in the field. The project completed the construction of the system and successfully conducted performance tests in the building research establishment, Integer House Lab. It's a lab that consists of a home that's used for testing new technologies. And the objective of the trial in this home was to test coverage, latency, location accuracy, and electromagnetic exposure performance of both the millimeter wave and the visible light parts of the system, and to provide recommendations for improving the design and produce design guidelines for optimal deployment of the 5G remote radio light heads in the buildings. It therefore helps to solve the problem of broadband wireless access in buildings and promote the 5G standard. This is a picture of the integer home in the building research establishment, and we were on the first floor. And we were testing, mainly we were testing audio video streaming to ultra high definition TV service. And this was the concept of the system. It's we aim to provide a 10 gigabit per second Ethernet ring to light access points, which provide a 5G signal to support visible light and millimeter wave access points. And this most of the aim was also in order to keep the footprint of the electronics small, to put most of the signal processing in the what we call the intelligent home IP gateway access point. This is the architecture that transpired from that. You can see the 10 gigabit per second Ethernet ring. You can see the RAN split between the upper layer processing and the lower layer processing. You can see the millimeter wave and VLC modules. You can see the layer 2 processing here, and you can see the OpenStack intelligent home IP gateway server here with the multi-source streaming, location, security, and transcoding virtual network functions, and the OpenFlow switch operating, and their interfaces to the internet and the 5G network. In order to, one of the main aspects of the system was that it could provide location data. So we achieve this by using a splitter, so that the splitter sends the same IF signal to 4 remote visible light access points, and that we can use a switch within that system to switch between each of them, so that we can measure received signal strength data from the user terminals. And similarly, for the millimeter wave, we would have a switch here that selectively chooses one of 4 millimeter wave access points, so that we can measure the time difference of arrival from each of the remote radial light head access points. So here's the setup with the frame. You can see that the switch. This is a subframe for a 5G, and you can see that for OFDM symbols 11, 12, 13, and 14, we selectively switch between the 4 lights, so that the user terminals only receive from OFDM symbol 11 from one of the lights, and therefore it can obtain receive signal strength data from that, and by triangulation be able to obtain its position. Similarly, for the millimeter wave, we send a pseudo-random noise sequence on the 14th symbol of a particular OFDM frame, and that is sent to just one of the radial light head receivers, millimeter wave receivers at a time in each of these first 4 slots, and that's used to obtain the time difference of arrival information in order to obtain location information from the devices. This is all represented in this system here. Each of the RAN, the user equipment reports its received signal strength data to a location database. The RAN reports its time difference of arrival data to the location database, which the location server accesses and produces user equipment location information at this point here, using this algorithm here. I presume these slides will all be made available to the delegates, so that they can look at the detail of what I've written on the slides in their own time. Okay, so that's the architecture in brief. So here is the integer home first floor layout. It consists of a sitting room area, a kitchen area, and an entrance hall area, and a conservatory type area. And, here is Kareem, one of our research assistants, on the RV user terminal, taking a millimeter wave measurement from the. In here you can see the 4 remote radial light head system, and in the background you can see the layer 2 processors and the OpenStack server. So we took measurements at ground level, but also we took measurements at tabletop level. Here you can see Ben and Kareem. Ben is now using a visible light communication receiver to measure the location accuracy, and Kareem is recording the measurement. Here you can see the remote radial light head. In the middle is the communication LEDs, and the outside are the illumination LEDs. And in these corners here, this is supposed to be the millimeter wave antenna, but we located them outside of this access point because we wanted to experiment with them by angling them at different angles. Here you can see a close-up of two views of the antenna, side view and front view. The antenna has been made, a cheap version of the antenna, made out of PCBs in order to make it like a consumer product. What we found was that we needed to angle the receiver towards the transmitter, both for the VLC and the mmWave measurements, in order to get better results. And so we quickly 3D printed a 2 degrees of freedom gimbal in order to be able to hold the measurement point steady while making the measurement. And we adapted it so that it could also be used for the mmWave antenna. And we also made a little 3D printing so that we could angle the antenna at 0 degrees, 30 degrees, 40 degrees from the vertical. This is the front end of the VRV test terminal user interface, where you can see the amplitude phase diagram here, the power delay profile, and the EVM evolution with time. These are the parameters of the transmission system. The mmWave required 3.5 gigahertz IF signal, and we were operating at 40 gigahertz. And the visible light would require a 15 megahertz IF signal, and we're operating within the visible light spectrum. And so we'll be using 64 QAM for mmWave and QPSK for VLC. We originally had intended to use 60 gigahertz, but because the components from the US were very expensive and being delayed for the delivery, we switched to a 40 gigahertz system. But the whole concept of the system was that it would be all operating in license-free spectrum, so that nobody had to ask anybody for permission to operate it. So this is what we obtained for the visible light coverage with the light, communication LED pointing straight down, and the receiving photodiodes pointing straight up. It had about 0.6 meter diameter coverage. Its maximum propagation distance was 2 meters, and this limited coverage is attributed to the physical construction of the photodiode sensor housing. So once we built the system to angle the receiver, we obtained a better diameter, which was a 1 meter. We continued to have a 2 meter propagation distance, and the variation of performance between the 4 light heads was attributed to the variability of the transmitted light intensities, which we couldn't change without a special tool from our colleagues in China, which we didn't get in time, so we weren't able to modify these. But we can imagine that they would have the same performance once we increase the intensity of the light. This was the coverage area and measurement map we used for measuring the location accuracy. So we took some measurements of location accuracy where we angled the photodiode receiver towards the LED transmitter for each of the measurement points. And we sent this information to our colleagues in Paris who used an artificial intelligence software to work out the optimum position of the anchor points in order to minimize the errors of the difference. And the results were that we were able to get the smallest location error of 0.55 centimeters, the average location error of 5.28 centimeters, and the highest location error of 11.9 centimeters, with 80% of all the location measurements below 10 centimeters. This is the measurement grid that we use for millimeter measurements, and we first of all pointed the antenna, transmit antenna vertically down, and receive antenna vertically up. And we made measurements at 0.7 meters above the ground with the receiver angled and not angled. And we saw a slight improvement of results when angling the receiver antenna towards the transmitter antenna. And the asymmetry of performance was attributed to a glass door on one side of the coverage area, which produced the mmWave reflections that impaired the performance of the receiver. And we did this at also 0 meters above the ground, and so with and without angling the receiver antenna towards the transmitter antenna. And we noticed that the performance at 0.7 meters was better than at 0 meters because the table shields the reflections from the floor, thereby getting better performance in this setup than it is in this setup. Yeah, so after we did the visible light measurements, we moved on to the mmWave measurements, where we pointed the antenna straight up without angling, and with angling. This is a floor. I can't see what the title is. Yeah, this is pointing 30 degrees from the vertical, and with and without a receiver angling. So this is angled and this is without angled. And we saw that angling the this is receiver non-angled. This is receiver angled. We found that angling the receiver improved performance. But we also found that there were variations during the day, so that we couldn't explain. And this is from the measurements that we obtained at 0.7 meters on the tabletop, with and without a receiver angling. And you can see that with angling, we obtained pretty good results. The reason why we stopped at 2 meters is because the synchronization cable was not long enough, but we expected this to be able to continue on for about 6 meters. And the performance of the mmWave does improve with the receiver angling towards the transmitter antenna, and it improves near the location of the transmitter antenna with backscatter. So you can see here that this is the position of the transmitter, and there's a certain amount of backscatter that also exists. So the antenna doesn't have to be placed right against the side of the wall. The performance of the mmWave antenna does improve a little bit with 40 degrees angling from the vertical, but not as much as the 30 degrees angling. So what we can say is that we obtained 42 megabits per second VLC system with a 10 megahertz bandwidth for 4-QAM and subcarrier distance of 30 kilohertz on the VRV test bed. We had a coverage of about 1 meter by 1 meter. The average location accuracy was around 5 centimeters. With the mmWave, we got a maximum bit rate of 310 megabits per second, 64 QAM and subcarrier spacing in the VRV test bed. And the Brunel test bed, we got a 70 megabits per second on 100 megahertz bandwidth using 4 QAM subcarrier spacing of 30 kilohertz. And the mmWave coverage area was around, probably around 2 meters by 6 meters. We got also measured 0.5 milliseconds latency between the user terminal and the external point of the RAN operating at 10 megahertz bandwidth. The remote radio light head and DRAM controller designs could be enhanced to operate at 400 megahertz and 64 QAM, thereby producing something like 1 gigabit per second per room. This is a scalable system, and so we can go up to 32 remote radial light heads with one gig for each of the rooms, up to 10 gigs as a total. We also performed field strength measurements, and this was done by the Building Research Establishment, and they first used FICO and WinProp simulation tools to estimate the extent of the electromagnetic radiation within the room and its effect on humans. And then they went into the room and took these measurements using these very well known state-of-the-art NADA EMF safety measurement devices. And we found that in the end, the results were well below what the safety measurements required. So we were very happy with that. So the VLC conclusions is the current system capabilities are suited to personal area networks, e.g. trains and planes. Maximum bandwidth needs to be able to increase from 10 megahertz and 42 megabits per second by a factor of 10 to make it a viable competitor for millimeter waves in home. The maximum distance needs to increase by from 2 meters by a factor of at least 2 or 4 to 4 or 8 meters. The maximum aperture angle needs to increase from 60 degrees to 120 degrees. The maximum aperture angle of the photodiode also needs to be more like have the characteristic of a fly's eye, so that it can have multiple receptors pointing at different directions, thus providing a broad range of field of vision. And a Fresnel lens could be used for that. And location accuracy were maintained by manually switching between the communication LEDs. This needs to be autonomously rated. A millimeter wave system, we need a minimum of 4 of these, and access points can provide a coverage of a sitting room area of 4 meters by 6 meters. The latency is 0.5 milliseconds. The measurement campaigns need to be performed on circular and dual vertical or horizontal polarized antennas. The uplink was not integrated on the VRV Brunel test bed, but we managed to get it working in the Brunel test bed, which paves the way for time difference of arrival measurement tests. The location of the 4 millimeter wave antennas do not necessarily need to be integrated with the lighting system, as their transmission propagation properties are quite different. And the best location of the 4 millimeter wave antennas is in the 4 corners of the room. And then further experiments are needed to be performed for the 4 transmit antennas to show that this man-made multipath environment does away with the requirement of angling the receive antenna towards any one of the transmit antennas. The exposure conclusions can be summarized by saying that they're well within the recommendations from the ICN IRP exposure limits that they have recommended for sustaining human health. This project was funded by the European project. Thank you very much. And there is a video here. I'll leave the link with you. So the video shows us working in the home in the building research. That's it.
Oh, thanks a lot, Professor John Cosmas, for a very nice presentation with a flow of things.
Yes.
So, and now I request Professor Anand Srivastava to kindly make his presentation, and we are at 3 o'clock now. So every 20 minutes, so we'll have 10 minutes left for a small question answer session. Yeah, Professor Anand.
Hello, good morning, good afternoon, wherever you are. Thank you, Professor John, for that interesting use case of VLC and millimeter wave. Real good practical demonstration. But my talk is going to be little general in the sense that I want to explore how VLC can be used in beyond 5G and future 6G. So I'll just briefly explain what are the direction, what are the challenges, what is happening. So the flow of my talk is start with 6G vision and then see how VLC fits in this vision. And then different technologies using optical wireless. It could be any band, not necessarily visible band, but it's a generic term, optical wireless communication technology. I'll be using OWC for this. And then what are the main building blocks of OWC networks? What are the research directions and what are the challenges? And finally, I'll conclude. So it's a good slide on vision of 6G. Wireless communication networks. So basically it is aiming at global coverage, which includes satellite, UAVs, terrestrial, and maritime as well. So it basically covers globally. There's a global coverage. And it is going to use all spectra, sub-gigahertz, millimeter wave, terahertz, and optical. Professor John discussed about millimeter wave and optical. So basically all spectra will be exploited in 6G vision. And it will include full set of applications using AI, big data. So a lot of machine learning will happen, which will actually, improve operational intelligence, environmental intelligence, or service intelligence of the network. And then strong security, both at physical layer and network layer. So 6G wireless, 5G, we know it has enhanced mobile broadband, which is popularly called as eMBB, or MMTC, which is massive machine type communications, ultra reliable and low latency, URLLC. Whereas 6G is going to combine some of these things, and then the kind of goals or the objective they have set is really very, very challenging. So they have come out with some enhanced mobile, or you can say eMBB plus, which basically combines both reliability as well as low latency, so which is termed as mobile broadband reliable low latency communication. Also massive machine type communication combined with low latency, which is referred as massive ultra reliable low latency communications. And then 5G talks about quality of service and quality of experience, whereas you are going to have an immersive experience, and the parameter which they are targeting is quality of physical experience, QOPE, which is actually a combination of quality of service and quality of experience. And it uses all three C's, that is communications, computing, control, and also localization. Professor John discussed about localization for using VLC and millimeter, and then sensing. And also energy of a small device through wireless energy transfer. So basically what I'm going to discuss under this head, the whole thing will take a lot of time, but I'll be focusing on the optical part here. How optical can be exploited for 6G vision here. So just to tell you the total electromagnetic spectrum, you have RF spectrum and visible spectrum, and you can clearly see here visible spectrum is 3 orders of magnitude more as compared to RF spectrum. So you have tremendous spectrum available here, and which is free. So, but one has to develop devices which can make use of this spectrum. But there is no scarcity of spectrum. So these are some numbers regarding RF and optical spectra. So RF basically goes up to 300 gigahertz, which includes high frequency or microwave and millimeter, and these are the ranges which are given here. And then you have the optical spectrum, which starts from 300 gigahertz, which goes to 30 petahertz, which includes IR, infrared. Again, there are different subsections of infrared, far infrared, thermal infrared, short wavelength, near infrared. And then you have the visible light, which starts from 394 terahertz to 833 terahertz. And then you have the ultraviolet, which goes up to 30 petahertz. So the applications of optical wireless, you can find in any range. For example, you can find this in chip communication, which is called as ultra short range. You're communicating between two chips using light. And then you can have applications in short range, which includes wireless body area network, or underwater, or within a flight. So this is some short range. I'll give you some numbers for these maybe in the next slide. And then you have the medium range, which basically includes vehicle to vehicle communication. The headlights of the car will communicate with the, either the street light or the traffic light, which includes vehicle to infrastructure communication, and VLC for local area networks and indoor IR. And then if you go little a higher distance, then you have free space optics, wherein you can use this as mobile backhaul. Instead of laying a fiber, you can use FSO, free space optics, as mobile backhaul. And also this has been used in ultra long range, which is space communication, two satellites communicating with each other through light. So it finds application, optical wireless finds application in all, depending on the distance, in almost all these applications. So basically, there are four basic technologies which will be used for different applications. So one of them is VLC, which is basically a physical layer. That is, there is a light emitting diode at the top, and then there is a media, there is optical wireless channel, and then you have a photodetector. So it can be your laptop where you have the dongle, which has a photodetector. So this is a VLC, visible light communication. So if you include both uplink communication as well as downlink, and also include mobility, handovers, then you actually land into Li-Fi, which is similar to Wi-Fi, and it has all features which Wi-Fi has. So this is light fidelity. And then you have OCC, that is optical camera communication, where LED light at the transmitter is communicating either through VL, visible light, or infrared with the device camera. So this is sort of unidirectional. And then if you want to use for backhaul applications or long distance application, the free space optics is another type of optical wireless communication technology. And it uses IR or visible light or ultraviolet, depending on what kind of distance you want, what kind of data rate you want. So these are the four architectures which will be used for different applications. That is visible light VLC, Li-Fi, and OCC, optical camera communication, and free space optics. Well, this basically covers the comparison of the two. So quickly I will go. Let me use that pointer here. So yeah, so communication topology, VLC has both unidirectional and bidirectional. Li-Fi has to be bidirectional. OCC is generally unidirectional, and FSO is both unidirectional as well as bidirectional. The kind of range you have in VLC is 20 meters. For Li-Fi, it is 10 meters, which is good enough for a room. And OCC is 60 meters. And FSO, you can have, satellite to satellite communication, few thousands of kilometers. In VLC, there can be a mobility support. Li-Fi, there has to be a mobility support. I mean, the user is moving from one place to another, so it has to support that handover. Then OCC is an optional. Free space optics is point to point, so there is no mobility there. Environmental effect, VLC indoors, because it's a deterministic channel, nothing happens inside the room. So indoors, it is pretty convenient to have VLC without having any environmental degradation. Whereas in outdoors, when you're using outdoors, because of environmental, the communication will suffer. So one has to, model the channel accordingly and design the system accordingly. Li-Fi, same. Indoors, there is no challenge environmental effect, but outdoor, yes. OCC is again indoor technology. FSO is surely a outdoor technology. So there are again challenges here. The interference level is low in all the cases because it is light communication. It is not going to interfere with any RF or anything like that. And the data rate which has been achieved so far is 10 gigabytes, which is pretty high for a LED, light emitting diode, which you have in your house or in your office, or 100 gigabit using laser diode. I mean, if you want to have high data rate, one has to use a different source, which could be a laser diode. Similarly, for Li-Fi, similar speeds. OCC, still people have not achieved high, communication, but 55 megabits have been achieved. And FSO, 40 gigabits, a distance of few kilometers has been achieved. Where the security in all the optical wireless technology is very high because the light is contained within the environment and it is generally line of sight. So it's very difficult to tap the light. So it's highly secured communication, which is one of the main requirement of 6G. So this basically tells you the data rate versus distance, which I had explained in earlier. So you have low speed short distance, low speed long distance, high speed short distance, high speed long distance. And these are some of the applications here. You have mobile communication or positioning. Underwater is low speed long distance. And then you have medical and security for high speed short distance. And then for indoor, you have ultra high speed short distance. And the private network space, it is actually going beyond 1 kilometer. That is why I've shown here going beyond 1 kilometer. So high speed long distance. So basically it covers all possible combinations of speed and distance. This is a specific case of using optical VLC or optical communication underwater, because ultimately you want to integrate with the maritime environment. So this is just a brief comparison between RF, acoustic, which is currently used, but optical, if you see, in terms of transmission distance, there is issue as compared to acoustics, but attenuation is distance dependent in both the cases, but it is less as in optical. The speed is high of light. Acoustic is very, very slow. Transmit power, you require just few watts for optical. Cost is low because you use normal optical components and for the transmitter and for the receiver. Data rate, which has been proven, is up to gigabits per second. Low antenna size. Latency is in optical is low compared to acoustic and RF. So optical is going to find a very good use case in underwater wireless communication. So this is just a schematic of a future underwater, light communication network. So these are important to achieve 6G network integration. Underwater is required. So as shown in this figure, interconnection of ocean observation sensors, ultra high speed non-contact data communication among different marine equipment, and functional implementations such as wireless fusion networking of submarine optical cable networks and underwater wireless optical communication all require support from underwater communication technologies. So this is quite important here. So compared with underwater wired communication, underwater wireless communication is desired because it does not require the transmission media and is currently which is currently being implemented by acoustic and RF. And I had told you the example, the advantages which optical will have as compared to RF and acoustic. So the basic building blocks of a OWC network, optical wireless network, I mean, whether you are using it for underwater or you're using it for space or using for terrestrial, indoor or outdoor, you have the basic device and components. Now these device and component depends what is your application. Then you have the optical front end, which is the transmitter and the receiver part. And then the channel modeling part. I mean, channel modeling, for example, underwater or space or outdoor, they're all different. So channel modeling is another building block. And then data transmission techniques, what kind of data what kind of modulation you are using. And then there are many users, for example, inside the room. So what kind of MAC protocol you are using. And then you have, light coming from different sources. How do you handle the interference part and how do you support the mobility? And then finally the networking protocols. So just a few, about the, what are the devices and components. So as I told you, for example, let me go here. So these are again, different bands here. And then as I told you, you have, high spectrum here, but then you have to have a device which can be modulated at that speed. So that modulation actually basically comes from this bandwidth of the device, basically comes from this expression, which is a simple expression, C delta lambda by lambda square, where delta lambda is the emission spectrum and lambda square is the operating wavelength. So suppose I take, this blue light at 600 nanometer, and emission spectrum of that blue light is say 0.45, and then I can achieve a bandwidth of close to 350 gigahertz, which is quite high. But then making such a kind of device is challenging. And similarly, this is the responsibility of the photo detector, which collects the light. So if you just put in some standard values here, you will see that it requires, 0.5 amperes per watt, or 0.5 milliamperes per watt per milliwatt of optical power for responding, which sometimes may be low. So there are advanced devices like avalanche photodiode or single avalanche photodiode, which are under development to meet.
Sorry to interrupt, Professor Srivastava. We have about 5 minutes left.
Yeah, I'll try to close this. Yeah, okay. So yeah, I'll just go rather quickly here. So optical front-end systems. Now, when you are using laser diode, you have to be careful about the eye safety standards. Your mobile terminal is changing orientation all the time, so you have to ensure that you get enough light at your receiver so that you are able to communicate. The large area detector, if you use, it will be limited in frequency, because large area means you want more power to be collected. So you use concentrators. And then in order to increase diversity, one is required to use angular diversity transmitters and receivers. Channel models, there are a lot of challenges here. You have multipath propagation in visible light communication. So you have to clearly understand what is line of sight, what is non-line of sight component. There'll be temporal spread, which will lead into intersymbol interference. And then reflective of the material, which is a function of wavelength. So what kind of material you have, which are the reflecting surfaces inside the room, and then whether you are employing this in a in a room or in a factory, or that kind of scenario. So accordingly, you have to model your channel. Data transmission technique, normally people use intensity modulation for this thing, but nowadays they are shifting to coherent because it gives you additional advantage, but the cost of complexity. And then on-off keying is the normal trend for low data rate, but if you want to increase high data rate, one has to go for OFDM. So a lot of research is happening using OFDM for optical communication. Then, carrier carrier-less amplitude phase modulation. There's another modulation which basically, has OK on-off keying, but at the same time, has high spectral efficiency, but at the same time has intensity modulation. And then one exploits special dimension in terms of having MIMO systems and number of wavelengths which can be multiplexed to give you high data rate. So this is combination of microcells and RF small cells. So if you have one additional layer of optical cells, so the data can be offloaded to these optical cells, which are called as attocells, and you are able to increase the overall throughput of the system, having one more layer of cell, which is actually optical, and where attocells is very, very small. So you can have reuse of frequency spectrum and thereby increasing the throughput and coverage. So this is medium access protocol. So these are the parameters one has to study. There can be different type of configurations, peer-to-peer, star, and broadcast. So one has to maximize throughput, all this packet delivery probability, and node active time. So these are the recent experiments, what has been achieved so far using VLC using white LED or phosphorescent white LED or micro LEDs. Using LEDs in underwater, using laser diode in underwater. So you will see, people have achieved 10 gigabits, few tens of gigabit for all of these applications. There is a fast development happening. In the last 4 years, a lot of development has happened and people have achieved about 20 to 30 gigabits for all these applications. So these are the material and devices which you require if you want to go to high speed and want to meet 6G visions. So these are special LEDs. I'll not go into the details. And similarly, you have special photodiodes here, and then combination of transmitter receiver. In both the things have to be integrated into transceiver. And once the research goes to the limit, then people will start probably working in switches and multi-mux and demux for VLC applications or modulator, all in optical domain. So these are the challenges. I mean, you have challenge from the light sources, you have challenge from the receiver, you also have challenges from the baseband processing, you have challenges from point to point, and then you require large lens groups. So these are some of the possible solutions. For example, for large lens, there are nano-optical antennas which you can beamform, use Fresnel lens, and you can steer based on using nano-optical, and then use of MIMO and use of SX for baseband processing. So these are some of the possible solutions where active research is going on. And machine learning is going to be very, very important in VLC. There are a lot of issues in VLC, nonlinearity, modulation format, indoor positioning. So when using VLC, you can enhance the performance. These are the challenges here. You have to have frequent handover because the lights are everywhere. You have to switch from one place to another. So this is going to be a challenge. A lot of interference because the autocell, the size is very small. There's loss in the atmosphere, and uplink is still not fully matured. Low data rate for OCC. Flickering, the light sometimes may flicker, so one has to design systems to avoid flickering, and then data rate improvement in fiber space for backhaul systems. So finally, I conclude here, VLC for beyond 5G and 6G technology platform is there, and there are a lot of applications VLC can be put to, and so it is going to support heterogeneous network, having high data rate and promising reliable security. But there are challenges which include interference, issues with ambient light, handover issues, intercell interference, backbone design, and how do you design VLC for very, very high data rates. So just final, I come from IIIT Delhi, and this is a state university by an act of Delhi government. So we have all these 6 departments, computer science, electronic, computational biology, human-centered, social sciences, mathematics. So it is all IT-centric institutes, and we have a lot of research centers, Center for Excellence in VLC and Li-Fi, which has been supported by TSDSI and European Union. These are the areas of research happening in IIIT Delhi, and most of them are related to VLC, which includes vehicle-to-vehicle, indoor communication, Wi-Fi coexistence, and some fiber-based stuff like fiber wireless architecture, elastic optical networks. And this is the Center of Excellence in VLC and Wi-Fi, which is recently started. And the activities which we are going to do under this Center of Excellence is workshop, training programs, invited talks from EU experts, and collaborative visits within Center of Excellence and EU partners, attending standards committee meetings, development of massive online courses, product hackathon, and ultimately contributing to the standards. That's the ultimate goal. So that we want to play a very active role in contributing to the standards of VLC optics Li-Fi. Thank you very much. I'm sorry I jumped the time. Thank you very much. Mr. Mittal, over to you.
Thank you very much, Professor Srivastava. So it was a very nice and informative presentation. So we have now about 6 minutes left. So I have a couple of questions, and we have a couple of questions in the question box. I will put a question to Professor Cosmas. I saw that you have used the frequency millimeter wave at 40 gigahertz, and also the subcarrier spacing as 30 kilohertz. So would results have been different if you have chosen a different millimeter wave frequency and the subcarrier spacing?
Yes, we originally wanted to use 60 gigahertz because it's a free spectrum. I think if we had used infrared, we probably would have got better results for the the optical wireless communication. And we've got a new project, as I explained in the chat, called 6G Brains, which is trying to use the infrared in a duplex channel, and hopefully we get better results, longer propagation distances. I'm not sure if the aperture angle will be any better, but certainly the bit rates will be increased as well because it has a wider bandwidth. So The advantage of the visible light, optical wireless communication over the millimeter wave and other frequencies is it doesn't exhibit so much reflections. So in an industry 4.0 environment, and that may be an advantage because there is a lot of metallic surfaces in factories which provide a lot of reflections, which you know, we experience this in a home, you know. So, but it'll be much worse in a factory.
Yeah, true. Thank you. Now, my next question to Professor Srivastava is, and then you can, Professor Cosmas can also add, that what we are looking for is high bandwidth and low latency and communication. So ultimately, these networks will have to integrate with the mainline networks like 4G core or 5G or even in future networks. So what has been done till now to integrate this apart from the testbed as a specification or interface development basis to integrate VLC based network with the mainline network like 5G, NR or NSA? Professor
So
Srivastava.
this a question is for me. Okay.
Yeah.
Okay. So currently VLC is still in its initial stage. So that integration with existing technology is yet to be done. But sure, the development, whatever development is happening in VLC or Li-Fi, always, designers, they keep in mind that ultimately it will be integrated with the existing network. It has to be backward, compatible. So right now, these are in the, initial stages, test bed stages, and, demonstration in the labs and all that. I mean, we have yet to see the deployment of these technology in the network. So it will take some more time because standards are also, under development. And, once we have the standards, probably, the system development will become faster, and then we'll be able to integrate with the existing network. But as I mentioned in this thing, this goes to a next level of technology, VLC, in terms of speed, in terms of security. So there VLC is going to play a very, very important role. Yeah. Thank you.
True. So thank you for that. And we have only 2 minutes left, so we can take one question which was there from the audience side, Mr. Samar Shalendra. And the question, those.
Mr. Mittal, the questions are already answered by Professor John. So
Okay.
if Professor Anand has a view on it, maybe you can see the tab in the answered. You can read the questions from there.
Yes. So I think the question is answered because the question is, what is the current penetration of VLC? Is VLC likely to be adopted as a future alternative of 3GPP? So I think right now, what Professor Anand said, it is already answered that we are in the very initial stages of developing this technology. So it can't be definitely be a replacement of 3GPP. Professor Anand, you want to add something?
Yeah, so just want to add, I mean, it is not that VLC is a technology which is a revolutionary technology. It replaces all the technologies. I think initially the technology will coexist. For example, suppose you have a Wi-Fi router in your home and you also have a Li-Fi. So both will coexist and you will have advantage because, Wi-Fi gives you a wide coverage and low speed, whereas Li-Fi, the coverage is limited because you have light, you have to be below the light and all that. So, but it gives you high speed. So if you are in a room where both Wi-Fi and Li-Fi there, you basically switch from Wi-Fi access point to Li-Fi access point or Li-Fi to Li-Fi. So both kind of handovers, vertical and and horizontal handovers are possible. And using this, you will achieve high throughput. So basically, these technology will coexist. So VLC is going to be a complementary technology. I don't think it is going to replace any other technology in the near future. That will not happen.
Yeah, right. So I think we are right at 3:30, and
I have one comment.
Yeah.
I have one comment. It's very interesting because when we first tested our system, we tested it in a VRV lab, which is a bit like a factory environment. And we found that even when we pointed the transmit antenna in the opposite direction, because there were so many metallic surfaces, we still got a very good received signal. You see, there the millimeter wave and those type of frequencies a lot of reflections, which may be in not advantageous in a factory environment. So this, I think, may be where optical wireless communication could play a good role.
Yes, I think Professor Cosmas, this is a very wonderful observation from this test that reflection is something which can be avoided compared to millimeter wave in
Yes.
this optical band. And it's a
Yes.
big use case for the factory environment.
If they can get a wider aperture and a longer propagation distance, may be most suitable in an industrial environment.
Mr. Mittal, maybe we can take one last question. There is an anonymous critical question which says
Yeah,
about why Li-Fi is not commercially popular even after so many years. Is it cost or technology? I think it's a good question to end the webinar.
Yeah, so Li-Fi, hey, again, as I told you, it will take some time because the kind of LEDs which we have, they have some limited, modulation bandwidth. And if you want to have high speed, basically you have to change your design of the LED. I mean, you have to meet both the illumination requirement as well as the speed requirement. But the kind of LEDs which are there, they were designed with illumination in mind. So I think industry has to change and make the LEDs which are both illumination as well as communication compatible. So I mean, things are happening, and then standards have started coming in. So maybe at physical layer and MAC layer, the standards are already there. Initial standards are already there, and if you want to use Li-Fi in a house, so you have to use some sort of dongle or some sort of mobile phone which should support both, cellular. We should have both cellular interface as well as light interface. So currently, those companies, they are still, looking for solutions which are cost competitive. Only then they will integrate in their network. So the research is going on, and I mean, maybe a couple of years down the line, probably you'll start seeing Li-Fi at least inside the offices or inside the rooms. So I'm very hopeful. Yeah, thanks.
so I think it has been a wonderful session, and good questions came, and it throws up a lot of hope that this VLC will one day will be a reality, and it will be integrated with the existing technologies. So thank you very much, Professor Cosmas and Dr. Anand, for nice presentations and these question answers. And I hand over to Mr. Sachin for the final closing remarks.
Thank you, Mr. Mittal, and thanks again both the professors for your knowledge on the topic. I think it's quite an emerging topic, and as Professor Anand also shared that the project is supporting a center of excellence in his institute, and Professor Anand is planning some initial workshops already in the coming months, where the idea is to build much more hands-on knowledge. And I think, Professor Anand, if I may also take the liberty to say that you are also open to connect with much more industry and cross-border collaboration. I think it will be interesting to see how this research area will emerge in time to come.
Yeah, sure. We are interested in joining hands across the border, within country, and also participate in a big way for towards making standards for this technology.
Yes, indeed. So we are looking for bringing the standards perspective. So we definitely invite all of you to come and participate and share your knowledge and expertise in how technologies like VLC can be integrated into a bigger pool of standards of 3GPP, for example. And with this, I would like to thank again all the experts and also the participants. We will be sharing the slides. I think the professors have no objection on our website, and we will also try to edit the sound quality of the initial presentation and see if we can remove the noise. Sorry for the inconvenience if there was any. So with that, we can conclude it. Thank you, everyone.
Thank you very much for inviting me, and the pleasure's been entirely mine.
Thank you very much, Sachin and Mr. Mittal. Thank you very much, and Professor John. Yeah.
Thank you so much.
Thank you.
Have a nice day.
Yeah, thank you. Thank you, everyone.